In section 8.9, we're going to explore the voltage relationships in a Y-configured three-phase system. And at first, that might sound sort of removed from anything very practical. But what you're going to discover when we go through this is there's this relationship that a lot of, say, experienced electricians that work with three phase, maybe they've worked with it all their life. They have lots and lots of experience, and they know these certain numbers that exist. For instance, they know this number 1.71, and that's a number that will occur and reoccur throughout this study. And anytime that you're looking at three phase electrical machines, power, that sort of thing. What we're going to do is we're going to find out that magic number that those that are experienced use, this 1.71, not only is it the square root of 3, and we're going to walk through how that's derived, but also the other relationships that makes that applicable to this Y configuration. And before we're done, I'm even going to show you some things that you thought maybe when you were in math class that you would never use, like the law of sines or the law of cosines. And we're going to make it relevant, make it real, and sort of take it at that level of understanding. Now, I will say that as you move through your studies and say you go beyond here at Central Piedmont, this is one of the few opportunities you're going to be able to see where some of these numbers come from. All right, so let's dig into this. Okay, so as we're looking at this figure 813 in our textbook, it's showing a Y-connected stator winding, the phases that we were looking at earlier and of generated voltage. And what we want to see when we look at this is, I want to point out a couple of things to you, okay? First off, here's phase A, here's phase B, and here's phase C. Now, along with that, what I want you to see is this neutral connection. So what we're looking at basically is a three-phase, three-wire system, like we looked at earlier. What we want to explore in this section, and we want to go through and derive that, is we want to understand what the voltage from phase to neutral is, and we're going to call that line to neutral. And we also want to know what the voltage is from phase to phase. Okay, now that would normally be designated, for this particular case, it would be A to C voltage. Okay, so again, just to give you, this would be C to N. And of course, this would be phase B to C, and so forth and so on. So that's the type of designation that we use. All right, so what we're going to do here, and this is important so you don't get lost in the terminology, this will be line voltage, this is line voltage measured as phase to phase, and this is line voltage measured from phase to neutral, or as they say, line to neutral. All right, with each one of these, we also want to always be able to follow the nomenclature that's used. So if I'm looking at a voltage EAN, I'm looking at that voltage from here to here. If I'm looking at this voltage, it's EBN, it's from here to here. ECN, it's from there to there. Now I can also change this. I could take this vector and I could draw it in this direction, and we'll do that in a minute. That voltage EBN that is changed in that direction now becomes voltage in ENB. Okay, so some basic things that maybe you've done in a physics class, where you're adding vectors, that sort of stuff. Okay, so just sort of laying the foundation there as we go through this. Okay, again, these are effective voltages, and they are represented, by the length of the phasor. And then what we're able to derive from this, and this is, um, we're going to work toward this in just a second, but we come up with these relationships that are given to us at the bottom of page 165. And I won't write them all down, but let's write down one so we can look at this. Here's 8.1. And it says that voltage EAB is equal to EAN plus ENB. Okay, so what does that mean? Okay, so what he's saying when he does this, he's saying that this vector, okay, is equal to EAN plus ENB. All right, now how would we do that? Well, the way that you do that is, you do this manipulation of this and from tip to tail. And so what he's done, see, what we're ultimately trying to figure out is what is the voltage from here to here, okay? Well, how do we do that? Well, one way you could do that with vector addition is you can take this, reorient it such that it would fit here, right? And that EBN now becomes minus EBN, okay? And that's what he's written here, in 8.1. All right, so EAB becomes EAN minus EBN. All right. Now, if you don't understand that, or you're like, gosh, I forgot that in math, I'll put up some, reviews on how you go about doing that. But, again, just let me, do a quick overview of that again, just in case, you say, gosh, I haven't done that in forever. So what we're trying to determine is this voltage. Okay, it is comprised, or what we can get that length, if we're thinking about this in terms of, um, geometry, by adding this plus this. These are vectors. They have magnitude and direction. Vector addition, to be able to add those two, to discover what that is, it is the sum of EAN, right, plus EBN. And to be able to do that, to find out what this number is, the way that I could do that is to orient it like this to be able to get that value. Now, where do these angles come from? Well, we know that this angle here is 120 degrees, right? And if we know that these are equal, then that has to be 30, that has to be 30. And so we've got the solution to that, from the triangle rules and laws that we understand, where, the total has to be 180 degrees. Okay. And so, 8-2, I want to know what the voltage EVC is. Excuse me, the phase voltage from here to here. Okay. Again, that is going to be given to us in 8.2, which is EBN right here, plus ENC here, which I'm going to change, because to go through that process, I would write that like this, okay? And then that follows through with 8.3. I'll just go ahead and do that too, since we're here. What is the voltage from A to C? and that's going to be equal to ECN plus this voltage here, which would be ENA, right? Which I could rewrite as this. Okay. Now, shoot me a note or email if you don't know what I'm doing right here, or if you've forgotten this, or you need some review on that. All right. So let me pause this for a second, and I'll see if we've got time to finish this one, or we'll make this part one. Yeah. So we'll make two videos here, but what I want you to see is this final figure here, which is figure 813D, and notice, you know, that we've done this addition. We've done it 3 different times so that we can make this determination of what the voltages are. And again, what we're looking for here, and this is actual practical real stuff, is in a 3-phase Y-connected system, there's going to be a relationship between the phase-to-phase voltage and the phase to neutral voltage. And it will be something that we will observe, we will measure, and we'll see its consistency. And I just want to go through that with you and let you understand how that's derived. Now, once we derive it once and we figure it out, you know, we'll just roll with it, and you know, we won't go through this level of discovery every time. Okay, so let me end this for 8-9.